Hello again everybody, once again this is Morgan from RacerX Performance Tuning, and I'm here today with my 1995 Mitsubishi 3000GT VR-4, affectionately known as Stickers. Today we're going to talk about tuning a twin-turbo 3000GT, or Dodge Stealth, to put down 500 all-wheel horsepower. So what does it take to take a stock VR-4 with its roughly 250 all-wheel horsepower and essentially double that wheel horsepower? Basically, two things: upgrades and tuning. Now, if you've watched our video earlier this year where we pushed the limits on a stock 3000 GT, you learned a lot about the combination of turbos and fuel delivery that the Mitsubishi engineers put into the original car. But if you want to get beyond those limitations to increase the torque and horsepower, you'll have to upgrade a few things, primarily turbos and fuel delivery. Now, before we talk about those things, I want to throw a word out there. And that word is called equifinality, which means there's more than one right way to get to your destination. So what I'm going to talk about here is my opinion based on my experience owning and tuning a lot of these cars, but that doesn't mean that it is the only way. So I've owned Stickers for a long time, and my good buddy Jeremy Sharp of Remy's Rides and I've upgraded a lot of it over the years. However, one area we have not upgraded is the bottom end. So Stickers is still running on the original 27-year-old pistons, rods, crank, etc. Everything on the bottom end. That's important to note here as we're talking about a 500 horsepower goal. Personally, I believe it is fairly easy to get these cars into the 400 horsepower range with just a few modifications. With some more, you can get into the 500s. However, once you start aiming for the 600s, 700s, and more, we're talking about a big boy build where you're going to need to upgrade all of your bottom end, as well as other areas of the car, just to support the massive amount of torque and horsepower that you're going to be putting down. I'm going to list all the upgrades we have on Stickers currently down in the details section below. Ultimately, your vehicle's horsepower is going to come from a combination of all the upgrades that you've made. Some of them will be more significant than others, but at the end of the day, all of them are going to contribute to your car's power. For example, having a good free-flowing exhaust system will decrease the back pressure, resulting in less exhaust pressure on your wastegates. In turn, that will allow them to stay closed longer and increase your boost and allow you to maintain that boost longer. Another example is your clutch, because once you start making, say, 400 foot-pounds of torque or so, the stock clutch is going to start slipping. If you don't upgrade that, it won't matter how much your turbos are putting out because you're never going to be able to deliver that power to the wheels. You get the idea. Now, having said that, the two primary upgrades that are going to be necessary to get into that 500 horsepower range are going to be turbos and fuel support. Without going into a tremendous amount of detail we discussed in the past video, the limitations of the TD04 9B turbos that come with the car. You can upgrade to 13Gs and probably break into the 400s, but if your goal is 500 horsepower, you will need at least TD04 15T turbos or something in that area. Now, Stickers is running on 16T billet ceramic coated turbos. A lot of our customers are running Arashi or Kinugawa 20Ts, both of which provide a lot of support above and beyond 500 horsepower. As well, I'd recommend the 3SX Executioners. So with the upgraded turbos, the mistake a lot of people make is that they upgrade just the turbos and expect to suddenly start making a lot more power. But in order to spin those bigger turbos faster, you will have to supply a lot more fuel. And that starts with upgrading your fuel injectors from those stock 360cc to, let's say, a minimum of 750cc injectors. And that's if you're running pump gas, maybe a pump gas with meth injection or race fuel. If you're going to be on E85, then you're going to need a minimum of 1000cc injectors. Bear in mind that the higher octane fuel you run, the more boost and the more timing you'll be able to add without running into knock. So fuel choice is also a factor in how much horsepower you can make. Now, in order to support those bigger fuel injectors, you're going to need a bigger fuel pump. Again, a minimum would be the standard upgrade to, say, the Denso or Walbro 255 LPH pump, along with a hot wire kit and an aftermarket fuel pressure regulator. So with the bigger turbos and increased fuel delivery, you'll have enough power in your hands to dramatically change your car. However, unless your car was built in 1998 or 1999, you're going to need an aftermarket ECU in order to tune the car to handle all that additional fuel and the bigger turbos. And here's the thing, a very important thing. You can get to 500 horsepower or more on practically all of the available aftermarket engine management systems for the 3000 GT. That means you can get there with flash tuning on a Jester Chrome ECU. You can get there on a standalone like AEM, whether that be version 1, version 2, or Infinity. You can get there on Megasquirt, you can get there on Haltech. You get the picture. Each of these engine management systems has things that make them unique, but they all also have a lot of things in common that we as tuners use to create more power. So if you're looking to get these parts to upgrade your car, I'd recommend you pay a visit to our friends at 3SX or IMR America. They have years of experience supporting these 3000 GTs. Okay, so that's all I'm going to say about upgrades. And remember what I said earlier about equifinality. There is more than one right way to get there. So let's get this car up on the dyno and talk about the tuning. So as you know, at RacerX Performance Tuning, we do a lot of remote tuning as well as the local tuning. And now everything that we're going to do here on the dyno, essentially you can do something quite similar with a closed private road. As long as that road is straight, flat, has no curves, and essentially you can repeat the same wide open throttle pull over and over again, so you can have some consistent pulls to be able to repeat the similar process. As many of you know, we did some tuning with stickers over at DBW Motorsports with Doug Wilkes last year on their Mustang dyno. At that time we ended up around 475 horsepower or so, and my goal here would be to see how much we could improve on that. Hello everybody, good morning. Once again, this is Morgan from RacerX Performance Tuning, and today I actually get to bring my own car to the dyno. So we've got stickers strapped down on the all-wheel dyno at counter steer. Going to work on a few things. I haven't had a chance to get to tune stickers in a while, so we will see what we're getting, what we can get, and you know, just have a little bit of fun here with my own car. So yeah, gonna get going here. We're gonna work on fuel first, which we actually did a fuel run already and it seemed to be pretty good, so that's great. Then we're gonna work on boost and then timing and see how far we can go. So here we go. Let's take a brief moment and give a shout out to our friends at Countersteer. Dylan Crumley and the team at Countersteer are renowned experts in the Nissan Skyline platform, doing everything from repairs to upgrades to fabrication and tuning. They are your one-stop shop for all things for your Nissan Skyline. Their facility is equipped with a DynoJet all-wheel drive dyno, and that is the very dyno that we use at RacerX for all of our local customers. One way you can look at the tuning process is to break it down into steps. The first step is always going to be fuel tuning. We take care of our injector scaling, battery latencies, do all of our start, idle, and closed loop fuel tuning before we work on the wide open throttle fuel tuning. From there, the next step is to do boost tuning, and then finally MBT, or minimum brake torque tuning. We start off by doing a series of what I call wide open throttle baseline pulls. Here, we want to start by turning off all the boost and retarding the timing tables by several degrees. The point here is that we want to just focus on the fuel delivery and not have any other variables interfering. Now, in order to ensure that we're running only on the wastegate spring pressure, we have to go into the ECU management system and make sure that we remove any and all wastegate duty cycle that the ECU may be providing. This happens to be an AEM, but the principle in the process is going to be similar regardless of what engine management system you may be using. So in this example, obviously this is a little bit of a variation on the hybrid boost model, but essentially what we could do here is we would just take all of our boost target compensation, and since we're adding 50 in the base wastegate duty cycle table, we just come down here and say, well, we'll say all of these values will be at minus 50. And essentially 50 and minus 50 is going to equal 0, and so then we will have absolutely no wastegate duty cycle coming out. If you're not using this sort of variation on the hybrid boost model theory, and then all of these values would essentially look something like, these might be set to 0. And then you can come into your table up here. So you were manually manipulating all the wastegate duty cycles at the various boost levels and RPMs. And again, you can just set all of these guys equal to 0. And you have the same effect, essentially 0 wastegate duty cycle coming out. Just for good measure, although it may not be necessary, you can come over to your advanced boost table and make sure you zero out all of your boost targets. So here we had a boost target of 13.3 based on the vehicle speed sensor. And again, same thing, just select all the values and set them to 0. And essentially there'll be no boost commanded whatsoever. This is how you're going to end up running at wastegate duty cycle. Next, we'll go over to our ignition tab, and here's where we're going to go in and severely retard the timing. Now, the way we're going to do that is we're going to essentially go in all of the areas that are in positive manifold pressure here. So in this case, it's going to be from 28 psi down to about 3.5, and we'll take off about 4, 5, 6 degrees of timing here. Let's take off 5 degrees here, and that's going to bring us down quite a bit. And then from there, obviously we want to keep things smooth in our table, so we'll do a little bit of linearization or vertical interpolation here just to kind of keep the map smooth. So what this is going to do is it's going to take timing out of our equation, allow us to go ahead and do that wide open throttle pull without any timing being a factor. You do want to be careful here a little bit though. You don't want to reduce timing too low, otherwise you end up sort of like that little bit of an anti-lag effect, and essentially you get what's known as boost creep. It will show up at the end of your RPM run, so be careful as you look into that. When we do this, we're going to have a lot of valuable information available to help us. First, we're going to be able to find out exactly what our wastegate spring pressure is. This will be the lowest possible boost that we can run. We'll also be able to see what our car's baseline horsepower and torque values are. This is essentially the car running at its weakest power level. It's always good to know where you're starting from, so you can see how much the tuning process adds to the car's ultimate power levels. So having taken out all the wastegate duty cycle and retarding the timing, we're going to make that pull on the dyno, and then we can look at our results. So what are we finding here? First thing we found out down here at the bottom is that our maximum boost was 11.24 psi. So basically 11 psi is the most that we're going to make, and if you look across the line here, looks like it essentially stayed at about 11, maybe rolled down to the mid-10s. As we move down a little bit further here, I guess that's it. Yeah, so it stayed pretty much around 11 psi. So that's our wastegate spring pressure. We know that it's 11 psi, and we can never go below that. Then at the top here, we're looking at our maximum power. We know that this car, without any wastegate duty cycle, without any timing, is making 334 horsepower and 307 foot-pounds of torque right out the gate. So this is where our starting point is going to be, and we're going to see where we go from there. We'll also be able to use all this information from our wide open throttle baseline pulls to determine the knock floor, and of course to do all the wide open throttle fuel tuning. We can also use the data from these baseline pulls to determine basically our knock floor. Now, how you do that is you'll basically go in and take all the raw values, the knock cylinder 1, 2, 3, 4, 5, 6, if you're using a sequential system, or just a knock 1 raw value if you're not, if you're using a waste spark system, and go in and just basically chart all this data at 800 RPM, at 1600, 2400, 3200, and all the way up until you reach your red line. What we're going to be looking for is what's the average voltage, or essentially the average noise that the knock sensor is pulling up at these various RPM levels. It is going to get noisier as you go up in RPM, and if you have a built engine, it's going to be noisier than a non-built engine. Point here is to determine what those average points are and put them into your knock sensor calibration table. This way, if you are experiencing knock voltage that is above and beyond your knock floor, your knock control system will come into place and start reducing timing or adding fuel, or both. If we take all our data from our data log and dump it into Megalog Viewer, we can make a number of charts that can help us to evaluate essentially what's going on during the course of our wide open throttle pull. So we'll have areas here where we're going to look at all the fuel characteristics that we want to evaluate. We've got knock information here. We've got wastegate duty cycle and boost targets information here. At the bottom here, we've got the RPM and the throttle position, and then some other things: ignition timing, injection duty cycle, and some temperatures. So essentially, when we scope out the part of our pull, we can see that we're going wide open throttle here from the beginning of this log all the way to the end, and the RPMs are going up from, say, about 3,000 all the way to the end here, which is about 7,000. And that's the range we're looking at. We'll focus in specifically on a couple things. One, as always, every time we do a pull, we want to go in and evaluate if we've got any knock. So this car is on a sequential system, so we're able to do knock per cylinder. So I've got all 6 knock cylinder values here. Obviously, I'm expecting to see zero knock information, and that's exactly what we got. If we're finding that we get any knock here at all, we've got retarded timing and no duty cycle for the wastegate, then we've got a significant problem. We got to take a step back and see what's going on. So this is just basically a sanity check here. We shouldn't see any knock at all during this pull. So now focus on the area that we came here for, which is the fuel. And if you see this red line and white line, they're basically overlapping each other, which is a really good sign. It's essentially saying that our O2 target and our actual O2 values are pretty much in sync with each other. Now, stickers was previously tuned, so I'm not surprised by this. But if the car hadn't been tuned, we should expect to see some variation here, and we'll go in and manage that. As we're looking across the pole here, at the beginning of the pole, we see that our O2 target was 11.9, and our actual O2 was 11.78. Pretty good, and you can see the lines are pretty much lined up with each other. Moving down, the target was 11.9 again, and our O2 is actually 11.9 as well. So right on target with each other. Moving further down the pole, still target's 11.9, and we're at 11.8. Let's come out here further. We're at 5,600 RPM, still at wide open throttle. Our target was 11.9. We're just a little bit lean on it at 12.0. Really nothing to worry about here. So again, this looks really, really good. If I see these two lines overlapping each other, I have a feeling that things are going rather well. What I can expect is that at some point in time previously this car wasn't tuned, that the red line and white line would show some discrepancies. And that's going to help us identify where we need to go into the fuel map and start to make some changes. Also, we can look at our histogram here. And with the histogram, we set this up so that we're looking at engine load, and we're looking at RPMs across the x-axis. And right here in the middle here, I just have the O2 averages. So we can see that at 2,900 RPM, and we can see that the maximum engine load was 10 PSI, because we knew our wastegate spring was only at 11. So we were running 12.04, and as we went across the RPM range, went to 11.9, another 11.8, 11.4, 12.05, and so forth. And again, this is kind of information that we're going to look at, just a sanity check. We go in and we can use a calculated field that you can have, which is going to say, what's the discrepancy between my O2 target and my actual O2. And this value I call the flex fuel percentage. And essentially, we're looking for this number to be at about 100. Okay, so if the division between the target and the actual O2 value is right on point, then it'd be at 100.00. If it's a little bit higher than 100, or any number is higher than 100, then we know that our fuel is a little bit rich. And if we're below 100, our fuel is a little bit lean. What we're looking for is values that are obviously outliers here. We see 99s, 100s, 101. We're pretty much right in the ballpark. And that is reflective of what we saw in our log view, where the red and white lines were on top of each other. So far our fuel looks pretty good here. We go back and make some adjustments. The adjustments will be based on where we had discrepancies here in our AFR error percentage. We can then go back into the calibration and make the appropriate adjustments there. So for argument's sake, let's say that we found out that during the course of our data log, we found that we were running a little bit lean in some areas, or rich. Let's say we found out we were running a little bit lean at, say, 10 PSI at 5,300. We found that we were running, let's say, 5% lean. We're definitely going to need to add fuel here in this part of the fuel map to help us avoid a potential knock from running too lean. Let's say at 5,700, we found that we were running about 3% lean. So again, we're going to need to add fuel here. What I would do is I would go in here from 10 PSI all the way up to the top here and go ahead and add in that 5% that we need to do. So we'll just say 105 and use the Pro style, and that'll get us the 5% that we need to add in. And then at 5,700, from that 10.5 PSI, again all the way to the top of the map, we're going in and add in the 3% that we needed to add to kind of get us back in line with our fuel targets. Now, just doing these two alone, as you can see, will result in a little bit of a peak right here in our fuel map. We need to go back in and do some linearization, some vertical and horizontal interpolation to kind of smooth things out so we don't have these peaks and valleys. So we'll take that 5,700 down to 10.5 where we went, and we will go, let's say first, let's go and interpolate things from left to right. So from 5,700 up to 6,500 down to that 10.5 range, and we'll just use some horizontal interpolation. Will help us to smooth this out a little bit. You can see the change in the map there. And then we'll go from 4500 up to 5300, again in that same range, and do some horizontal interpolation. When we do that, we can see that we smoothed out part of the map here. We still need to go in the vertical direction as well. Since we made these changes from 4900 on up, from 10 psi, 10.5 psi, let's go back and blend these changes back down into the table, down from 10.5 to 3.5. This will help with that transition there. So we'll do a little vertical interpolation here, and that starts to smooth out that section of the map. From here, load this calibration onto our car, go back out and do another wide open throttle pull under these same conditions, review the data log, and we should see that we're now no longer running lean in these areas. And probably within about 2 or 3 pulls, we should be able to get all the values in our fuel map straightened out, and then we'll be done with our wide open throttle fuel tuning. Now, with the fuel tuning complete, theoretically, we should not have to worry about the fuel tables anymore, as neither boost or advanced timing should have any effect on the fuel. However, in reality, we will have to continue to monitor it and occasionally make some tweaks to it as we continue. With boost tuning, our goal, regardless of what engine management system you are using, is to find out how much wastegate duty cycle is needed to generate a certain amount of boost. Once we have these values, we can then easily program in our boost targets and then let some closed loop features add or subtract a little duty cycle as necessary to keep our boost pressure in line. You'll find that we can completely optimize boost across the entire power band by using a 3 or 4-point boost solenoid. So AEM gives you a number of ways to set up your wastegate duty cycle. Remember that word we talked about earlier, equifinality. There is more than one right way to do this. Now, in the boost tab, you've got these 3 tables. Boost wastegate base duty table, the boost target compensation table, and the boost error duty table. Now these 3 tables actually all work together with each other, but you could theoretically just go in and manipulate the boost wastegate base duty table and essentially go in and plug in some values for the wastegate duty cycle here that you feel would be appropriate to meet your boost targets, 10, 14, 17, and so forth at these various RPM levels. Go and do some pulls on the dyno and see how well you did and make adjustments accordingly. That is one way to do it, but I think it would be very time consuming and a little bit difficult to manage. Another way to do this is to use these tables together. So if we go in and let's say take all the values from 0 psi on up across the whole RPM range and set them to 50. Set 50. And then in the boost target compensation table, we also took all of the values here and set them to minus 50. Now, the effect that this is going to have is essentially if you have 50% wastegate duty cycle and you have minus 50% wastegate duty cycle, the end result of that is going to be 0% wastegate duty cycle. So essentially right now we're not commanding any duty cycle between these 2 tables. They'll kind of zero each other out. The next thing we can do is start to work on just the boost targets that we need to address. We know from the previous work that we did earlier, finding out our wastegate duty cycle was at about 11 psi. So everything from here, from 10.3 all the way back, we can leave these right where they are because we're never going to be able to manipulate wastegate duty cycle to be anything less than that 11 psi. So our next target up here is going to be 13.3. And we can make an easy guess here to just say we know we're going to need a little bit of wastegate duty cycle to get above that 11 psi, but not a whole lot to get us to 13. So we might go in here and just set this value to start off with, say, minus 40. That's going to give us about 10% duty cycle between the 50 that we've got here and the minus 40 that we're going to take away from it. Go on and set the rest of the values here across the rest of this table to that same minus 40. We'll begin to address those in a little while. So we're just about ready to go and make a pull on the dyno to see how this wastegate duty cycle is going to work for us. But we have to look at a couple other tables before we do that. The third table on this page, the boost error duty table, is essentially our closed loop. What this does is if we're below our boost target, it's going to add duty cycle up to about 25% here if we're 12.5% below our boost target. And if we are above our boost target, meaning we overshot our boost, it will subtract wastegate duty cycle and help to keep us from overboosting. A lot of people, a lot of tuners prefer to zero this table out while they're doing their wastegate duty cycle boost tuning. I actually like to leave it on because I think that the feedback that we get from this can help us to shape our wastegate duty cycle values a lot faster than we could without it. Finally, we'll need to move over to our Advanced Boost tab. And here we'll find 4 more tables that all work together as additives. So that's to say, together, these all tables add up to the boost targets that you're trying to get to. You can have opportunity to tune boost by RPM, by throttle position, boost by gear, and boost by vehicle speed sensor. Most of the time we start off with just doing this by vehicle speed sensor because it's an easy way to kind of just get all of this dialed in, and then you can manipulate things a little bit later on. So our first boost target is that 13.3 psi, so we can take all the values and set them to 13.3. So we know that essentially we're going to start to target 13.3 psi as we run through this pull on the dyno. Now that we made a pull on the dyno, let's go take a look at the results. As always, we take a little sanity check and just make sure we had no knock. Not expecting any, we didn't have any. Just checking on the fuel again, red line over top of the white line, and pretty much in sync is telling us that our fuel is still pretty good. We're going to continue to check this. What we do see is that there's a little bit of feedback, O2 feedback, subtracting about 4% here, maybe 5 or 6% later on. So it's something we can go in later and make some adjustments there. But I will just leave it alone for right now and see how things turn out as we add more boost and timing. So what do we really want to look at? We want to look at our boost wastegate values. Now let's see how our boost targets and wastegate duty cycle came out. We had dialed up in our boost wastegate map 50%, and in our target compensation map minus 40%. So together that's going to give us about 10%. Here it's rounded it. The value is 9.376 combined wastegate duty cycle. So we know we're commanding about 9-10% duty cycle, and we're going to see what that gives us. So what are our results? Well, let's see. Our boost target, as we noted, was 13%, 13 psi, and it's the same for the speed sensor, 13 psi. So these two lines over top of each other, they're matching. But what do we find out? Our actual boost was 10.582 psi. 10.582 psi is quite a bit lower than our target. In fact, we're about 3 psi lower than our targets. That's our boost error, minus 2.93, essentially 3 psi below where we're supposed to be. Okay, what can we do with this? Well, we got some information we can learn from this, right? We talked about this earlier. So our boost wastegate number 1 out, that's the amount of duty cycle that was actually being sent to the solenoid, was 15%. Now, that's not what we asked for. We asked for 10%, and we ended up with 15%. Why? Because our closed loop helped us. It said, hey, we're not getting there, and we need to add some more duty cycle here. So it added up an additional 5% to bring us from 10% to 15% duty cycle. And even then, that wasn't enough. So we look at our boost just stayed there flat at about 10.5 across the board. And we learned that 15% duty cycle, even though we thought originally 15% duty cycle was still going to be a little bit short. So now we can go back, take this information, and update our calibration. And we have something to tell us how to get a lot closer to our boost target. Coming back over to AEM, with the information that we learned from our data log and the analysis, we can make some changes. So here at that 13.3 psi target, we originally had added 10% duty cycle, and we found out that the 10% wasn't enough. The ECU used our duty correction file here, the table for closed loop, realizing we were below our target and added an additional 5%, which made us have 15% duty cycle, and still we were too low. So with that information together, we can go in here and let's add some more duty cycle to help us reach our 13.3 psi target. This time we'll go ahead and say, we'll set this as, let's say minus 22. Right? That's going to get us a lot closer to our target with the information we have. The beauty in this is that this is the only table that we need to change as we're making these adjustments. Before we had to go in here and make all these adjustments based on various PSI targets and RPMs. Here we just need to do it in one spot. So we're going to take this information, do another pull on the data on the dyno, and see what our results are. With our revised calibration, having made another run on the dyno, we find that we've got some really positive results. Again, quick sanity checks, we realize that we have no knock, so I'm not concerned about that. Our red and white lines for O2 and the O2 targets remain on top of each other, so that's also good. No changes in fuel as expected. Let's go and look at what we did with wastegate duty cycle. We had 50% duty cycle from the map, and we subtracted about 22% from the target compensation, gives us a total of about 28% duty cycle now. So before we were running 10 to 15, now we're running 28% duty cycle. Let's see the results. Our targets still remain the same at 13.3 psi, and now we're seeing that we're commanding 13.5 psi, so essentially right on the target that we were looking for. No boost error. Our total wastegate out is 28%, and there's no trim, means that the closed loop didn't need to do anything to adjust this. As we go across the rest of the pole, we will see a few variations, but overall, staying true to that result of the 13.3 psi that we targeted, very little boost error, very little closed loop correction for the ECU to do. This is the success that we're looking for, and this is how we're going to continue up the rest of the boost targets to finish out our wastegate duty cycle boost tuning. So continuing on with stickers, fuel is still looking pretty good here. Working up boost, so just working up the boost targets and getting the correct wastegate duty cycle. So we finished 13.3, we're working on 16.3 now, and then from there we'll go up to 18 and continue on up. So so far so good. 13 is accomplished. Let's go on and knock out 16.3. And so we went about continuing the boost tuning process in that same fashion. So we found out that we needed to move up a little bit to get to 16.3. Then we targeted 19.3, 22.8. Then finally we settled in at 25.8, or essentially 26 psi. Decided not to go further than that. We could have looked at 28, 31, or beyond. But there's a reason why I decided to stop at about 25, 26 psi. Now the beauty in this approach to boost tuning is that you end up only having to work with the one table, the boost target compensation table. We get to leave this wastegate base duty table alone and don't have to go through the rigmarole of trying to edit all of these values and interpolate and manage all of that. Simply working on your targets and using the boost target compensation table allows you to get the exact wastegate duty cycle for the boost targets that you want. Then you end up going over here just into your advanced boost tab, and then you can set your targets that you want to achieve at various vehicle speeds or target RPMs, target throttle position, or boosting by gear. So the only thing you're going to see here that I've done additionally is here at the end. And as I mentioned, all four of these tables work as additive. So these things together will be added up to be your boost target for your wastegate duty cycle. So essentially, we know that when we get toward the end of the RPM range, we're going to start to lose boost. One way to kind of compensate for that is by taking your boost target RPM table and slowly adding a little bit more boost as you get toward the higher RPM. It won't always work, but it will try to keep the wastegate duty cycle up there to allow that pressure. Now, as I mentioned, we decided to cap things at 25 psi. What does that entail for us? So we're looking right here. We had a 32.8% target boost compensation combined with our 50% base wastegate duty table. Essentially, we were running 83% of our wastegate duty cycle to get to this 26 psi. Now, could we have added more boost? Yes, but we don't need to. A lot of people, tuners included, think that they need to run as much boost as possible to get the most power from the car. Now, we can continue to make more power while simultaneously prolonging the life of our turbos, right? And that comes with timing advance. So boost and timing complement each other. We're going to see that here in just a moment. But let's see the results of what we got from the boost tuning that we did do. Looking at our results on the dyno, if we go back to when we made that baseline run, we can see that we were making, 334 horsepower and 307 foot-pounds of torque at that 11 psi. So right there was our baseline. And by adding, looks like we added 13 pounds of boost overall here at the end. When we look at the end here, we ended up getting to 410 horsepower and 376 foot-pounds of torque at about 25 psi. So just through adding boost alone, that 13 pounds of boost, we added 75 horsepower and looks like about 70 foot-pounds of torque. And that's not bad. So we're going to take from here and start to do the timing, and we're going to see what more power we're going to make without adding more boost and without having to change our fuel. Now we've reached the final stage in our boost tuning process, right? We did all the fuel. We haven't had to mess with fuel since then. We did all the boost tuning, and we shouldn't have to change that either as we move forward into timing. With advanced timing, we're going to work out to this thing that's referred to as MBT, or maximum brake torque. And what that means is we're going to try to get the most timing that we can run without running into knock. And once we've reached the fact that we can no longer make any more torque gains, that's the indication that we can stop raising timing. So we're going to look at that and see how we can maximize timing across the entire power range, the same way that we kind of did with boost. The interesting part and the most important part is we're going to have to really start to look out for knock right now. We didn't have any knock when we were doing fuel tuning because we didn't have any boost and we didn't have any timing. And we didn't have any knock when we were running into boost because we didn't have any timing. So for sure, now when we start to get to a certain point in timing, we can anticipate that. We are running on E85. If you're running on E85, race fuel, you're going to have a better chance at warding off knock than if you're running on pump gas. But in either case, you're going to have to look out for it and manage it when it arrives. Coming back to the ignition map, you'll recall at the beginning of the tuning process, we detuned a whole lot of this map, essentially taking out, I think it was 5 degrees we took out all the way from 0 psi all the way on up. Now, my general rule of thumb is to start by adding in 3 degrees at a time. And for this session, we'll start and add 3 degrees all the way across the top from 3.5 psi on up. We just simply push the add button, and we're going to add 3 degrees to all of these values. And then we'll simply go in as we did before and just blend it back into the table with a little bit of vertical interpolation. And that'll keep the table smooth, and we won't run into any issues there. So with this 3 degrees added back in, we'll be able to go and make the run with that and see what our results were. Okay, so this is our first timing advance. We're going to add 3 degrees across the top. We're going to keep the boost cap right there at 25.8. Evaluating our results in the dyno chart shows that the impact of just that 3 degrees of added timing is immediate and impactful across the entire power range. We went from approximately 410 horsepower and added in another 16 horsepower, bringing us up to 426. And on the torque side of things, we went from 376, adding in 30 foot-pounds of torque, bringing us up to 405 with just that 3 degrees of timing that we added. Particularly, we're going to be looking at the difference between the previous run and the next run each time we add timing. Here we can see that the red line to the blue line, there's a nice gap in between the two. And that shows a significant increase in torque that we're looking for. As MBT starts to get reached, we'll find that at some point in time, these two lines are going to line up together. Wherever they've lined up together, essentially at that point in time, we've maximized the timing that we could add for that RPM range. And we can stop adding timing then. There may be other areas of the graph that are still showing a gap, and we can continue to add timing in those areas until that gap goes away as well. That's how we're going to work toward MBT. Alright, so now we're going to add another 3 degrees timing from 3500 on up, blend it back in, and see what we're going to get. As we continue to add timing, we're going to start to notice that the gap between our torque gains slowly starts to decrease in certain areas. Here we can see from 3000 to about 3500, the gains are really shortening up here. And from 3500 on up, we still have room for gains to be made. This is where we've reached some minimum brake torque. Right here, we've kind of maximized the timing, and we can stop adding timing in this area of the map. Looking at the timing map, up until this point, we've been adding 3 degrees across the board from anywhere in the positive manifold pressure all the way across the whole RPM range. And we've been able to get away with that because every time we've done so, we've been seeing torque gains across the board. Now, once we've started to see that we're no longer getting torque gains, we have to stop adding timing in those areas. So, as we noted in the last dyno graph, we saw that from about 3500 on up or below, we were no longer making torque gains. So this area of the map, we're no longer going to start adding to. However, the other areas of the power band, we're still making gains. So from 3700 to the end of the RPM range, to red line, we're going to continue to add until we start seeing those areas go away as well. So the way we're going to do that is we'll take, say, from 4000, from 3.5 psi all the way to the end. And again, we'll go with our continuing to do what we've done before by adding 3 degrees. We'll add those 3 degrees in there, and then we'll just kind of blend it back into the table so that our map remains consistent. A little horizontal there, and then we'll do a little bit of vertical blending from here on down to minus 1.2. And that's how we're going to keep our map going. Okay, adding another 3 degrees, this time from 4,000 RPMs on up. Last run we got 475 horsepower, so we're trying to get up there. Looking at our results in the dyno chart, coming from run number 10 to run number 11. So run number 10 is in yellow, and run number 11 is in blue. We can see right now that we've really started definitely maximizing the brake torque and no longer seeing gains any part of the early part of the map. So here up through about, looks like 4,500 RPM, we've definitely maximized, and we will not be adding any timing there. You might notice a gap here in the lower RPM range and think that there's still room to be made. However, we started running into a little bit of a boost leak somewhere along the way. You can see there's a discrepancy here early on, and then things kind of get evened out later in the RPM range. So we definitely were losing some boost there, and that's a representation why we had less torque here. But essentially everything from the beginning of the run up through about 4,500 RPM, we've maximized the timing. As well, later on in the run, from say about 6,000 to the end, we've also maximized timing. So we just have this one little area right here in the middle that we can work on, and the rest we're going to leave as it is. Returning once again to our timing map, we know now that all the maximum brake torque has been accomplished up through about 4,000 RPM, so we're no longer going to be adding any more timing here. We also know that, let's say, above 60 or 6,000 RPM, we've also maximized the timing, so we're not going to be adding timing here. We've got a little bit of room left to work with, and that's just this small area right within here. Now, so we'll go ahead and add another 2 degrees. I start to get a little bit slower, not 3 degrees, but maybe 2 degrees at this point in time as we're getting pretty close. So we can add 2 degrees here, and then we'll blend it in again as before. Now, one thing that we're going to talk about while we're doing that, so let's add the 2 degrees in here. And we'll blend it from 37 up to 45. And then we'll blend it again from 57 up through 65. And the reason why I'm doing this blending is to keep the map consistent across the board. Now we'll just go back and once more blend this back down to the 0 line here vertically. So now we're boosting at about 24 psi, right? And you would think that all we need to focus on is this 24, maybe this 21 psi range, as we're not really boosting at 28 to 30. And we're not down here at 14 or 17 either. However, you do want to go ahead and blend things in with the map and keep the map consistent. In the event that you later on raise the boost up to maybe 28 psi, well then your timing and map is going to be in sync. And if you decide to lower the boost for any reason, you're also going to have your timing map in sync, and you won't have to redo this work. At the end of this process, we're going to start to see our run after runs on the dyno chart starting to look like this, where we can see that the torque is pretty much the same across the entire power band from the beginning of the run to the end with very few discrepancies. So essentially at this point in time, we've maximized all the timing that we could maximize and getting the most out of it. We do notice that there's a little bit of a dip right here on the second run, on run 16 here from the previous run. And we're going to talk about what that is and what happened here right now. Up until this point, we've been talking about MBT in terms of maximum brake torque and noticing when we've no longer made torque gains, and that being a limiting factor and an indication to stop adding timing. But however, the other part of the equation to look at is if knock starts to creep into the equation. Once we start seeing knock, that's also an indicator that we're going to have to not only stop adding timing, but probably take off 2 or 3 degrees to keep things safe. So in that last dyno, we saw that there was a little bit of a drop in the horsepower in the latter RPM range. And so what happened there? Well, we go back and we look and we see that we encountered some knock here. We're here right at about 6,237 RPMs is when we encountered a knock. Now, looking at the raw values, we can see that the noise is going to increase like normal, that it should do across the RPM range. As we're getting into the higher RPMs, there will be a little bit more noise. But we do see a few outliers here. And these are the areas where we're actually resulting in some knock retard that's happening in the system. So what happened here, right? We have a knock floor that's been established. Let's go and take a look at the knock floor briefly here. Knock floor. Here, looking at the knock floor that we set up, we can see that about 6,400 RPM, the floor is set at 1.1 volts, and at 7,200 RPM, it's a 1.2 volts. So if the knock sensor is picking up a volume of noise or a voltage of 1.1 to 1.2 and below, it's going to consider that to be normal and expected noise coming from the engine. If we're above there, though, then we're going to understand that this is an outlier and that this is an indication that there's some form of knock going on, and we're going to respond accordingly. So as we look at this in AEM data, we can see that on cylinder number 4, we had 3.19 volts, and on cylinder 5, we also had 1.49 volts. So the 3.19 volts is clearly 2 volts above our floor, and 1.49 is just a little bit above our floor. So now, Stickers is set up with a sequential ignition, so we are able to see the voltages across the various cylinders, and also able to do what we call knock per cylinder, which allows us to address just the cylinder or cylinders in which the knock is occurring and leave the remaining cylinders running at the same timing and fuel that they already have. However, if this were a waste spark system, we would just see the one knock information for just the knock across all of the cylinders, and the retardation or additional fuel would be across the board for all of them. So what happened here, when we received that that indication that there was an event outlying our floor here and here, both cylinders 4 and 5 responded accordingly. So 4 saw that we were 2 volts above the floor and took off 15 degrees of timing just from that cylinder alone, and added an additional 15% more fuel as a way to try to ward that off. And cylinder 5 in turn saw that we were just a little bit above the floor, 0.3785 volts above the floor. It also threw in some retardation, took off 2.5 degrees of timing, and added a little bit of fuel, again, to try to ward off that knock. And as we move across the remainder of this run, we'll see that this additional fuel and this retardation of timing resulted in the knock going away, and then ultimately all of the timing and all of the fuel was restored to both cylinders 4 and 5, and we continued the rest of the run. Now, this knock occurrence is more likely, or should I say less likely, the higher octane fuel that you're running. So we have options, right? We can be running 93 octane from the pump. We could be running 93 with a methanol injection. We could be running race gas, 103, 100, 101, 109 octane. And we could be running ethanol, like E85, which is the case with Stickers here is running ethanol at about 80%. I think on this run, we actually were about 70% ethanol. So the higher the octane that you're running, the less likely it is that you're going to run into knock. And so in this case, this was the only knock that we found all day with Stickers. So through this point, we were able to continue to add timing, and we found out that we got to the point where we couldn't add any more timing because we weren't getting any more additional torque gains. And in this one instance, it was the only time where we found that we, in this amount of timing, which was 32 degrees of timing, which is a lot of timing at that point in time, we actually ran into some knock, and so we needed to back that down a little bit to keep things safe. And that's going to wrap things up. Following this process, we're able to maximize the fuel, the turbos, and the timing advance to get the most power the car has to offer across the entire power band, while at the same time protecting the engine from detonation. We hope you enjoyed the video. Please feel free to leave any questions or feedback in the comments section, as well as to like and subscribe. Thanks again, everybody. We'll see you again in another tuning video, so stay tuned.